All right, lesson 4, common forces. Forces due to gravity. Now, this gravity is the same gravity that we were talking about in four fundamental forces. However, when Newton came about and tried to describe what gravity was, people really wouldn't understand it or couldn't understand it because they really couldn't explain, and Newton couldn't even explain why this one mass has to attract another mass, right? How could it happen? He could explain that behavior of it, and he could explain the effects of it, but he doesn't know why it does it, right? So people were sort of skeptical when Newton trying to explain gravity. But for now, as we know it, in Newtonian mechanics, gravity is a force between two objects, and it's attractive force. Now, when we are on the surface of the planet, this gravity is basically interaction between our body mass attracted to Earth body mass. Okay? That attractive force between our body mass or any mass near the surface of the Earth, right, gets attracted towards the center of the Earth, and we call that gravity. And we also call that gravitational force our weight force. So when we talk about our weight, we talk about our gravitational interaction between our mass and Earth mass. That interaction is called F sub g. This is not F times g, this is F sub g, it's a subscript. All right? And that F sub g, or force gravity, or force due to gravity, is equal to the mass times acceleration caused by that gravitational force. So sometimes A sub g can be represented as just g. Okay? Now this g has a direction always straight down towards the center of the Earth. Okay? So no matter where you are on the surface of the planet, down will be towards the center of the Earth, and up will be perpendicular to the surface of the Earth, straight up towards the sky. All right? When we talk about gravity, okay, it is a force, and on Earth, our gravitational acceleration will be 9.8 meters per second squared towards the center of the Earth. On the Moon, it will be 1.67 meters per second squared, and on Mars, it's like 3 point something. All right? So, depending on how massive the planet is, the gravitational pull will be different, and acceleration of the objects near those surfaces of the planet will be different. But the gravitational interaction also involves with distance, and we'll learn about that more later. And distance from the center of the Earth to the surface of the Earth, right, will be different than distance from center of the Jupiter to the surface of the Jupiter. So even though Jupiter may be much, much more massive, right, because the surface is further away from the center, it may not be as big as you think for the acceleration due to gravity. All right, so this 1 kilogram mass will accelerate at 9.8 meters per second squared downwards towards the center, and this F sub g will be then 9.8 newtons in the y direction, in the negative y direction, which is towards the center of the Earth. Therefore, the weight of 1 kilogram on Earth is 9.8 newtons. Okay? Average person is about 50 kilograms of mass. Okay? So, average person will have weight of 490 newtons. I know that sounds huge, right? But 490 newtons is really not as big as you think. All right? Same 1 kilogram mass on the surface of the Moon, right? Will have 1.67, right? and meters per second squared. So that same mass will only have weight of 1.67 newtons on the surface of the moon. Okay. Now, the direction, force of gravity, always acts straight down, even if the mass is on an incline. Okay. That means if I were to have a mass on a horizontal surface, okay. So here, horizontal surface, and I have a mass on that horizontal surface. Right? Fg will always be straight down towards the center of, right? So F sub g, which is equal to m times g, will always act straight down towards the center of the earth. Even if it is on an incline like this, your F sub g will always be pointing straight down towards the center of the earth. Okay? Even if I were to place this object up against the wall, right? If I were to place this object up against the wall, like that, the weight of this object will always be pointing straight down towards the center of the earth. So Fg, like so. Even if I were to put this on a ceiling, right? If I put this thing on a ceiling like this, right? The Fg will always be straight down towards the center of the earth. I hope I made that point clear. Okay? So whether it's horizontally flat on the surface like so, right? Or on an incline like this, or on a wall, or on the ceiling, okay? Doesn't matter. Fg will always point straight down. All right. So that was weight or gravity, force of gravity. Another common force that we should be familiar with is called tension forces. Now, tension forces happen through a string or a rope or a cable, okay, when you pull on it. Tension is a reactive force, which means it only happens when you pull on a string or a cable or a rope, okay? So, tension force pull, it never pushes. I hope you never try to push a rope because you're going to get hurt. You could only pull on a rope, okay? And tension forces always act along the string or the rope or the cable. So make sure you understand the tension will happen in the rope itself. Okay? And because it's a reactive force, something must pull on the rope to have tension in the rope. Okay? Don't get confused between the length of the rope versus the tension of the rope. You could have a very long rope, but if you pull on it very slowly or with a great small amount of force, the tension will only be very small. All right, just because the rope is long, it doesn't mean it has to have a long, big tension. Another thing is, contrary, if the rope is short, doesn't mean the tension has to be small. Rope can be very short, but tension can be huge, depending on how much it's pulled. All right, so don't let the length of rope confuse you from the magnitude of the tension itself. Okay? So when a tension is applied or the force is applied on a rope to create that tension, right? This tension is along the direction of the pull. Okay, the direction of the tension is direction along the direction of the pull. Okay. Here is Fg, which is gravitational force. Now, the table or the surface of the table, it has to support this object's weight. This support force is called a normal force. And this normal force, okay, this normal force is very important. This normal force is equal to the surface force of a table or the ground, or etc., right? Straight up 90 degrees from the surface. And this is very, very, very important. This 90 degrees, John. That means it has to be perpendicular to the surface. Okay? So, must be perpendicular from the surface. Sometimes it's also known as the supporting force. Okay? So if we had an object on a horizontal surface, so this is a horizontal surface right here, and if we were to just lay this object down on a horizontal surface without any other forces acting on it, gravity is the only force acting downwards, and in order to support this object's weight, the surface has to act up on the object with a normal force. Now notice this angle is 90 degrees from the surface. Okay? So this reacts to whatever the weight that is acting on this surface. If it is on a incline, like on a ramp or an incline like this, your normal force has to be perpendicular to the surface. So this right here is 90 degrees. Okay? It has to be perpendicular. It has to be 90 degrees. And so is this, right? 90 degrees to the surface. Notice this FG is still acting straight down on an incline, right? How much would this normal force have to be in order to support it? Would it be same as your FG here, or would it be less? Well, we could probably figure that out. Let's take it to the extreme. Let's make this incline like really like this, like make it really stand up like this, right? Then your object will have FG going straight down, right? So your FG will act straight down, even if it's steep. So this is your FG, right? Which is M times G. Your normal force will be from the surface to the object. And guess what? It's not going to be. It's going to get smaller and smaller. So here's your F normal. Okay. Matter of fact, if it's straight up like this against the wall, right? If it's straight up against the wall like this, your normal force goes to 0. Your FG is still straight down. But your F normal is equal to 0 in this case. Okay? So, the normal force, or force normal, is reactive force. And that is very important. Again, it's reactive force, not proactive. Okay? So if I were to push down on this object, with extra force, let's say I push down on it, what's going to happen to my normal force? Is it going to increase or is it going to decrease? Good, all right, yeah, okay. It will definitely increase because it has to support more force by this surface. Because he has to react to it. F normal always acts perpendicular to the surface, even if the mass is on an incline. F normal is not always equal to the weight force, because I could have more forces acting on it vertically downwards or upwards, right? It may increase or decrease depending on how the third force is acting on that vertical plane. Okay? It's so important. Okay? Let me see if I can find an example right here. See page 18 for example. All right. So, let's take a look at this example of normal force problem. I have 10-kilogram box of candy and it is resting on a smooth, frictionless horizontal surface on the table. So this table, there's no friction. Now, it doesn't really matter if there's friction or not, right? A, determine the weight of the box and a normal force acting on it, right? So this is A right here. So here's A. Now, here's how I would like you to solve this thing. This here, we know it as Fg, right? And this is F normal. There are no other vertical forces acting on this for part A. So for part A, right, we can say sum of all forces in the vertical direction in y is equal to m a y. And sum of all forces in the y direction is equal to, there are two forces. There's F normal and there's Fg. Okay. Now notice I put these vector symbols there. Okay. F normal is pointing upwards, and I'm going to consider the up direction to be positive. That means down direction is going to be negative. So if I set these two net forces equal to each other, right, because this is, look, identical to this. So this must be equal to this. So I can say M A Y is equal to F normal, positive. So I'm going to keep that as positive. Fg, downward direction, I'm going to keep that as negative. However, AY, so this candy is not going to be accelerating up, or it's not going to accelerate through the floor, so my AY is 0. So 0 is equal to my F normal minus Fg. So if I solve for F normal, right, my F normal is equal to, if I bring this to the other side, it becomes positive, right, Fg. And that is equal to 40 newtons. So my F normal in this case is equal to 40 newtons for part A. Okay? Now let's take a look at part B. Again, I'm going to consider up direction to be positive, down direction to be negative. And part B states, now you push down on the box. So here, I'm pushing down on the box with extra 40 newtons of force. Right? Again, determine the box's weight and the normal force acting on it. The box's weight, Fg, does not change because it's still 10 kilogram box. I'm sorry, should be 9. Sorry. This is actually m times g, and that is equal to 10 times 9.8, and that should be 98 newtons, not 40. Sorry. So the F normal should be 98 newtons. Okay, 98 newtons. So the F normal is equal to 98. Since Fg is equal to 10 times 9.8, there Fg is equal to 98 newtons. This doesn't change either, right? Because this, really, your Fg doesn't change because the mass is still 10 kilograms. Therefore, your Fg is equal to 98 newtons still for part B as well. However, for part B, I'm going to write it down here. For part B, okay, sum of all forces in y direction for part B is equal to MAY. And sum of all forces in the y direction is equal to, I have F normal, I have Fg, and I have force applied. I'm just going to call that F sub A, force applied, or force push, right? So I have 3 forces here, and those 3 forces are F normal plus Fg, right, plus force applied. So here, my MA, y is equal to F normal, positive direction, so I'm going to keep it positive. Fg, downward direction, so it's negative, so minus Fg. Force applied is downward direction of 40 newtons, therefore negative force applied. Again, the acceleration of my candy is not going to be accelerating upwards, or it's not going to be accelerating downwards. It's standing still on this table, so the acceleration of this candy is 0. So my force normal, in our case, minus Fg, we already know what this is. We already calculated to be 98 newtons, right? So this is minus Fg minus Fa is equal to 0. So if I solve for F normal by bringing these two negatives to the other side of the equal sign, my F normal then is equal to Fg plus Fa. So my F normal now is equal to 98 plus 40. So my F normal for part B comes out to 138. 138 newtons. So it's definitely more. Right? It's definitely more. All right. Now let's take a look at part C. Part C states, now if you pull up with the force, so here's my FA, this is my FA here, is 40 newtons upwards. Okay? So I'm going to consider up direction again to be positive. Okay? So the FA is equal to 40 newtons, upward direction. So for part C, again, Fg is still going to be 10 times 9.8, which is equal to 98 newtons for my Fg. So the weight doesn't change again because the mass didn't change. Okay? So sum of all forces in the y direction is equal to MAY. Sum of all forces in the y direction is equal to, I have F normal plus Fg plus Fa. Now, let's set them equal to each other. MAY is equal to F normal, positive direction because it's pointing up. Fg, pointing down, so it's negative direction. Fa, this time is pulling up, so it's positive. And since acceleration of the candy again is 0 vertically, I have my F normal minus Fg plus Fa is equal to 0. Now if I solve for F normal, my F normal is equal to, this becomes positive, this becomes negative. So this time my F normal is equal to 98 minus 40. So my F normal now is equal to 58 newtons. All right. So think about your normal force as what your bathroom scale would measure. Okay? Because if you were to place a bathroom scale right underneath this box of candy, okay? And let's say this bathroom scale only measures in newtons. So if I lay a box of candy that has mass of 10 kilograms on that bathroom scale, that bathroom scale would read 98 newtons. But that same box of candy weighing 98 newtons, if I press down on that candy with 40 extra newtons of force, the bathroom scale is going to read greater than 98, it's going to read 138 newtons. And if I were to give a slight lift on that candy box with 40 newtons of force, now my bathroom scale will not read 98, it's going to read less. It would only read 58 newtons of force. So if you think about it, think about the normal force as what bathroom scale would read if you were to place that bathroom scale between the surface and the object. I think that helps a lot of students when they think of it that way. All right, good. So that was page 18. Now let's take a look at page 16. Okay. For page 16, we have to understand another common force that we'll be using a lot and you should be familiar with. It's called frictional force. Frictional force is another surface force that acts this time parallel with the surface, where normal force acted perpendicular to the surface, friction acts parallel to the surface, okay? And resists the tendency for sliding, okay? Tendency for sliding. So the friction force is again reactive force, not proactive, okay? Unless you are in an accelerated frame of reference, but we're not going to worry about that, okay? So the friction force is a reactive force. So it's only present when there's some kind of a push against an object, right? Only present if push is present. And friction can be calculated with mu times the F normal. So this is the formula. Now remember this F normal? Yeah, this is important. So you need to calculate F normal in order to find friction. Okay? This funny looking U is actually a lowercase m in Greek letter mu, right? Mu. This mu, if you're from Kansas, you say mu. If you're from Mainline, you say mu with an attitude. But this actually is a lowercase m. So they sort of write it like this, like, but it looks like U with a tail, right? It's called coefficient of friction. This coefficient of friction is different depending on what two surfaces are rubbing against each other, okay? And this coefficient of friction, there are two kinds. There's one for mu sub s and mu sub k. Mu sub s happens when it is not moving. This is a static coefficient of friction. And this is when it's not moving. And this, mu sub k, is kinetic friction, or moving, when this thing is sliding across the surface. So there are two different kinds of friction, static and kinetic friction, okay? Now, numerically, the coefficient of friction is a ratio of two forces. And those two forces are basically friction, right? So mu is equal to frictional force divided by the normal force. So notice the frictional force has a unit of newtons. Normal force has a unit of newtons. So the units should cancel out and mu should be just a pure number. Okay, it's just a pure number. So you have to think of this as just a ratio of two forces. Now, every two surfaces in contact have their own value of mu. Okay? Now, higher the mu, more resistance. Lower the mu, less resistance. I always like to think of mu as level of pain, right? Threshold of pain. I mean, if you think about like, when you're taking a shower and let's say you rub your face against a nice smooth tile, right? All lathered up, you're not going to feel that much pain, right? So low mu, low friction or coefficient. But let's take that same face, right, out into the street, into the sidewalk, and put your face against that concrete sidewalk, and then rub against that concrete sidewalk. Yeah, I know. You'll feel a lot of pain. There might be some bleeding, right? High mu. Okay? So think of mu as high mu, lots of pain, lots of resistance. Low mu, no pain, smooth sailing. All right? All right. Let's continue with friction. Experimentally, it can be found that mu sub s is greater than mu sub k. Sometimes they're equal to each other, but most of the times, the static coefficient of friction is bigger than the kinetic coefficient of friction, right? And that's because if you ever try to like move something really heavy by pushing on it on a surface, or like rough surface, like let's say like you're trying to push like a refrigerator. It's like you push on it, it doesn't move, it doesn't move, it doesn't move, and then as soon as you budge it, it just starts to get easier to continue to move, right? Because it's probably inertia as well. So the friction, it's going to go up, go up, go up, and then all of a sudden, as soon as it starts to move, it drops down, and then it's easier to move, right? So, like push, 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 doesn't move, doesn't move. So as soon as it moves, it falls down, and it becomes easier to move with, right? So this is static part, and this is the kinetic part. Okay, so this is like mu sub k, and this is like mu sub s. Now, why is mu sub s different values, right? Different values than mu sub k? Well, it's not mu sub s is different. It is the frictional force of static friction that is different, right? And the frictional force of kinetic friction is different. But static friction has different values because it doesn't require all the frictional force to hold things back. So what do I mean by that? So if I were to have an object like this, and if I were to push on it, if this object or mouse has static friction of, let's say, I'm just making this number up, of 40 newtons of frictional force that can be calculated, right, as static friction between this mouse and this paper. If I apply force of 10 newtons, would this budge or move? If this thing has 40 newtons of force of friction that can be calculated? Okay, good. All right, you brought your A game today. I love it. No, it won't. Right? It's only going to stay because it doesn't have enough force to get this thing moving. However, and I'm applying 10 newtons of force that way, it only requires 10 newtons this way to keep it from moving. So my frictional static friction is only 10 newtons. This is it's going to react to only my 10 newtons of force. Now, if I'm applying 20 newtons of force, there you go, right there, right? Is it going to move? No, because my frictional force can go up to maximum of 40 newtons. But it doesn't require all 40 because I'm only applying 20 newtons of force. So the friction is only pushing back with just 20 newtons of force. Now if I'm applying 30 newtons of force, same thing. It's only going to react to my push, and it's going to react back with 30 newtons of force. However, when I apply 40 newtons of force, it will reply back with 40 newtons of force and still not going to make this thing accelerate. But soon as I go beyond 40, now it's going to actually accelerate. When it accelerates, if I apply 50 newtons of force, it's going to be accelerating because I have net force of 10 newtons going this way, right? However, now once it starts to move, you have to think about using kinetic friction rather than static friction. And kinetic friction is usually going to be less than static. So if this were calculated to be 40 newtons for static friction, kinetic friction, let's make up number and say it's going 30 newtons of kinetic friction. Then as soon as this thing moves, as I apply 50 newtons of force, instead of 40 newtons of force holding it back, it'll be only 30 newtons of force resisting it. So the net force will be now 20 newtons that way. Okay, so it is very important to understand that static friction is definitely a reactive force. Okay. Now, static and kinetic coefficient of friction are independent of surface area in contact. So it doesn't matter how wide the surface area is or how narrow the surface area is, it is independent. Okay? The value of mu is found experimentally. What type of experiments could you do to calculate mu? That's a good question to answer. So think about that and think about how you could actually calculate mu. All right? We'll come back to that. I'll give you a hint. Put it on an incline. All right, let's take a look at an example on page 17. So we have 10 kilogram object, okay, and it is subject to two forces, F1 and F2, as shown below. Now F1 is acting 20 newtons in the positive y direction, and F2 is acting in fourth quadrant, right? 30 newtons of force, 330 degrees. Okay? So if I were to pull on this 10 kilogram object simultaneously with two forces, what's going to happen to this? What's going to happen to this? So here, let's say I have 10 kilogram object right here. And I have two forces pulling on this simultaneously. One pulling this way at 20 newtons, another one being pulled this way at 30 newtons. And if I pull on it simultaneously, it went that way, as though only one force was acting on it. Right? So the net force is adding these two forces up to create that one single net force that acts as though only that one force is pulling on that object in that direction. All right? So first step you should do is always try to calculate the net force. Okay? So first, find the net force. And how do we do that? Well, we could find the force 1 and force 2 in a Cartesian form. Okay? So let's calculate what force 1 is going to be in Cartesian form. We know it's not going to be going in the x-axis. So it's 0 x hat, 20 newtons in the y direction. So it's positive 20 y hat. newtons. That was easy. But this is going to give us trouble. Why? Because this is not on the axis, it's up here. So this will actually have, right, x and y component. So here's your f2y, and you have your f2x. So how do I calculate f2x and f2y? Well, f2x is equal to f2 times cosine of, this is the angle theta, really, the proper angle, which is 330. So my f2x is equal to 30 times cosine of 330. And what is that? So here, 30 times cosine of 330, and I get 26.0, right? 25.98. So I get 26.0 newtons x hat for my f2x. And my f2y is equal to f2 sine of 330, right? And that is 30 times sine of 330, and that is negative 15 newtons y hat. You could fact check me, right? So 30 times sine of 330, and I get, boom, negative 15. All right, so my f2 is equal to 26 x hat minus 15 y hat newtons. When I add these up, okay, when I add these up, I get my net force. And that would be 26 x hat plus 5 y hat newtons. So my net force will be 26 x hat, 5 y hat. So it's going to go somewhere in this direction. Now obviously this is off scale because like this is 20 and this should be 15, so you should be like way down here, right? So here again, this is my net force. Okay? 26 5y. So what is the magnitude of that net force? The magnitude of net force is square root of 26 squared plus 5 squared. So the magnitude of that net force is equal to, right? So 26 squared times plus 5 squared, right? You have to square root that. So I get 26.5, right? So I get 26.48 newtons. So that's the magnitude of my net force. So this is 26.48 newtons for my net force. What about the direction? What about the direction? Well, this angle theta right here, right? Theta is equal to tan inverse of, right, the net force y over net force x. Therefore, theta is equal to tan inverse of 5 over 26. So what is that, John? So 10 inverse of, right, 5 divided by 26. And I get 10.9 degrees. Okay, I get 10.9 degrees. So this angle here is 10.9 degrees. Okay. Now we can actually answer some questions. Let's take a look at A. Find the acceleration of the object. Well, for A, since acceleration is equal to, well, the net force is equal to ma, so the acceleration is equal to the net force divided by the mass. Right? So what is my net force? My net force is 26.48 newtons, right? Comma, theta is equal to 10.9 degrees. Divide that by mass. What is the mass of this? It's 10 kilograms. So my acceleration is 26.48 divided by 10, which is 2.648 meters per second squared, right? Comma, theta is equal to 10.9 degrees. That's the acceleration. 2.648 meters per second squared. And it has to have direction because acceleration and the net force will have same direction. All right, what about part B? Part B. Find the third, if the object is at rest, at t is equal to 0, how fast is it moving after 3 seconds? So for part B, you know initial velocity is 0, right? You know acceleration now is 2.648 meters per second squared. And you know t is equal to 3 seconds. And I'm looking for VF. That's equation 1, right? Which is VF is equal to VI plus AT. So VF is equal to 0 plus 2.648 times 3, right? So 2.648 times 3, and I get my VF is equal to 7.944 meters per second as the speed of this. And it will be going in that direction. But since they only ask how fast it's moving, that's all we need. Now for the third, if I were to find third force to make this object not accelerating and make it static equilibrium, means no acceleration, which therefore the net force should be 0. All I have to do is just add this exact amount of force in the opposite direction of it at my F3, right? If I add this exact same amount in the opposite direction, so the angle here, from here to here, should be 180. So the total angle from here to here should be 180 plus that. So theta should be 190.9 degrees. And F3 should be 26.48 newtons. So my part C, F3 should be 26.48 newtons, comma, theta 3 should be 190.9 degrees. All right, any questions? All right. All right, I'll stop right there. And I'll see you guys on Wednesday. All right. Have a nice day, everybody.